Hello everyone. In this video, I will discuss the concept of circular motion. Now, to establish a foundation for discussing circular motion, we're going to talk about first the coordinate system for studying circular motion. So we know in a 1D motion, we can build an x-axis, and then the object's motion will be confined in that direction or in that straight line. So that's the 1D motion. Coordinate system. Now we know that we need an origin. Let's say the origin is here, and if an object is to the right side of this origin, then this position is positive. And if we draw the direction of the position vector, then it will be pointing to the right. Now similarly, if there's an object on the left side of the origin, then its coordinate x is negative, and that represents a vector pointing to the left side. So let's call this R1 and that's R2. Let's label these X1 and X2. And there it is. That's our coordinate system for 1D motion that we know before. Now, you may ask, why do I talk about this 1D motion coordinate system that we already know? The reason is because this circular motion, when we confine it in at a certain distance to a center point, then we say this circular motion is actually a 1D motion. So circular motion is actually a 1D motion. Although we put this circular motion in the 2D kinematics, it actually belongs to 1D motion. So let me show you why. So here is the circular path that we're looking at. And here's the origin O. And originally we think that we would need an x and y coordinate system to describe this object's motion. So now let's say that there's an object here moving in a counterclockwise direction, going this way. And you may think that we need both x and y. And indeed, that's true. We can use x and y coordinate to represent this object's motion. So let me build the coordinate system right now. That's x, that's y-axis. And if an object is here, then we say its position vector is this quantity, this arrow. And suppose that the radius of the circle is capital R. We're going to use this capital R just to represent the distance from the circle to the center. Then we can say this R here is represented by its magnitude is this capital R. Okay, and its direction, if I figure out this angle theta here with respect to the x-axis, then we say its angle is theta. Therefore, the vector r is given by capital R and angle theta. So that's the representation we talk about in the vectors chapter. And we also talk about the component form for this vector r. So now let's say this point is at the coordinate x and y, Then we can say this vector r is also given by xi hat plus yj hat. And sometimes we just write it xy. Okay, and that's a conversion between these coordinates, x equals r cosine theta and y equals r sine theta. So you may say now we have a two-dimensional vector, right? A 2D motion. However, because this r is fixed, so the only variable is the angle theta. And then the object can only move along this path. And if you look at if you think about this path here, it's effectively a 1D motion. So we get effectively a 1D motion. If we confine the object to be on this path only. Okay, so that's why we say that we want to review this first 1D motion coordinate system first before we talk about this circular motion, because it's effectively a 1D motion. All right, so now you may say, then what is the quantity or variable that we want to build the coordinate system for? Just like in the 1D motion, we have x-axis, x coordinate. Now here, we're going to use theta. As I told you already, theta is the only variable. So theta is the quantity that replaces x. So theta is going to replace the x in linear 1D motion. So we're going to have a linear 1D motion and angular 1D motion. Okay, so theta here represents an angular coordinate. So now let's think about the coordinate system requirement. Because we have an origin in the linear 1D motion, so we know that if the object is to the right side, then that coordinate is positive. So now the question is, do you have a similar definition in the angular 1D motion? So now the answer is yes. Okay, so here's the convention. Now we're going to use this x-axis as the reference line. And then the angle will be with respect to the reference line. So now let's say we're looking at the object right now at this position. Then we say its coordinate is going to be theta here, right? And then just like in the linear 1D motion, we have a positive position. Now this angle here is defined as positive. So I'm going to call this theta 1, similar to the 1D linear motion case. So this theta 1 is positive. Okay. Now if the object is measured from, let's say, this angle, let me call this R2 position, and then with respect to the reference line, the object's angular position now is theta 2 right here. Then we're going to say this theta 2 is negative. Okay, just like in the coordinate system, linear motion coordinate system, x2 here is negative. Now instead of talking about right side and left side, we're going to talk about clockwise and counterclockwise. So theta 1 is in a counterclockwise position, and theta 2 is in the clockwise position. So we're going to define this counterclockwise as positive direction, and this clockwise here we're going to define it as negative direction. Therefore, we have exactly the same correspondence from the linear 1D motion. Okay. Now you may say that how about I measure the second position R2 from this direction, because I can keep going, right? I can keep going from the x-axis, that's the reference line, in a counterclockwise direction, and I can also end up here. If I go this way, then let me call this theta 3. Okay, so let me say how about if I use theta 3 to represent position R2. Yeah, you're right, that's also true. So we can also say theta 3 is the coordinate for this position, and then that coordinate is positive. Okay, so both theta 3, which is positive, and theta 2, which is negative, measured in the clockwise direction, they represent the same vector R2. So they're actually the same. So you can write down, let's say R2 is theta 2 will be equal to theta 3. Okay, so these two vectors are actually the same. They represent exactly the same arrow that we drew in the picture. Okay, so that's the discussion of the coordinate system. And then after that, we will just focus on the kinematics first, and then we'll talk about the circular motion later on. Okay, so angular kinematics. Okay, so we start off with the angular position theta. Okay, and then again, you want to measure the theta with respect to the positive x-axis, and then you could have some positive value or some negative value. And then from there, we can define the angular displacement. We call that delta theta, which is defined as the final angular position minus the initial angular position. Now here's the illustration. So I'm going to draw this circular path again, and then now I only draw this x-axis, the reference direction, and then I do have, let's say, theta I, the initial position, the final position is here, and then that's theta final. So now theta final minus theta I will be this angle here. Oops. That's delta theta. Okay. That will represent the displacement. And then if I know the time instant is Ti, time instant is T final for these 2 points, then I can further define this average angular velocity. Okay, so now we can talk about the rate of change of the position, angular position. Okay, so average angular velocity symbol is omega, and we're gonna say it's average, and then it's delta theta, delta t, which is defined as this ratio here. Now, if I take the limit of delta t goes to 0, then we have the angular velocity, instantaneous angular velocity, which is d theta dt. All right, so that's the instantaneous angular velocity. Now, angular acceleration will be the second order derivative. So I'm going to write out these directly. So the symbol for angular acceleration is alpha, which is the omega dt that we have here, or the second order derivative of the angle. All right, so that's the some symbols we're going to use for studying angular kinematics. And just like the linear 1D kinematics, they have these several kinematic equations. So if the motion here is a constant acceleration, so let's say alpha here is a constant. Okay, so now let's see what kind of equation we have here. We first have the final angular velocity as the function of the initial angular velocity plus the angular acceleration times delta t. And so that's the velocity relation. So now how about the displacement here? Okay, so we can say the final position is given by initial position plus the initial velocity times delta t plus 1/2 the contribution from the angular acceleration, 1/2 alpha delta t squared. Okay. We also have the final velocity and the initial velocity relation. So related to the angular displacement. Okay. And lastly, the displacement, we also say the final position is initial position plus the average angular velocity times delta t. Okay, and we know the average angular velocity is the midpoint of this omega, right? So you can say it's the average of initial and final angular velocity. Their average is omega average. Okay, so that's the angular kinematics. All right, so now let's talk about the uniform, a kind of special motion called a uniform circular motion. Now the reason we call it uniform is because the angular speed or angular velocity's magnitude is a constant. If omega equals constant, then we say it's uniform. That's the definition of uniform circular motion. Okay, all right. So now think about the meaning of this, and then how do we use this condition to figure out the property of, so what kind of property do we have for the uniform circular motion? And by property, I mean what's the position? Meaning, how do I write down the theta here? And what's the velocity? We already know that actually. And what's the acceleration? Alpha. So those are in the angular coordinate system. Now, related to the previous linear motion, right? We also need to talk about what's the velocity here, what's the x and y coordinate here, what's the vx, vy linear velocity, and then the acceleration a. Okay, so what are these quantities as well? Okay, so I'm gonna first build a coordinate system, and then we'll start from there. All right, so that's the origin O, and then there's a x and y coordinate. Origin O is here, and then we already said that we just need this angle, right, which is the only variable to represent this object's motion. Right? However, it's helpful to also write out these x and y because we know the linear motion first. So it's better that we start from the linear motion x and y, and then we'll talk about the angular. Okay. And as I said in the previous picture, the radius of this circle is capital R, which is a constant. So that's why I can say the position R here is R and theta. Now I want to use the condition that omega is constant. Now we remember that the omega is defined as d theta dt. Okay, so just like the linear 1D motion, where the v equals dx dt, we can go from there and then figure out the theta, right? So theta is theta naught plus initial theta, theta I, plus omega times delta t. And if I pick the starting position here, so theta I will be 0. And one more thing here, I forgot to mention the theta, the unit here is in radian. Okay, so whenever we talk about angular linear motion, the angular position, the measurement should be in radian. So from there we have a 0 here, and then omega is just the t. Right? Let's say here is at instant t, and theta equals 0 at 0-second instant. Then we have that, right? We have this relation. So that's why I can replace theta by omega t, and that will give us the complete information about this r. Okay. However, I still need the x and y since I want to talk about this, right? So let's go over that. X is given by the x component. So let me draw this projection. So that's the x, right? That's the projection. And if the projection is to the y-axis, then that's y. That's y coordinate. Okay. So x equals radius r times cosine theta, and y equals radius r sine theta. Okay. Now in terms of the time variable, it will be omega t here and sine omega t here. Okay. Now we do know the velocity as a function of xy is given by vx is dx dt. So I simply just take the derivative of the previous expression. Now from there, I need to do derivative of the cosine function. That will give us a negative sign. It also brings out the factor omega to the front. So it's negative omega r sine omega t. when you take the derivative of this x expression. So Vy is dy dt, and it's given by omega r cosine omega t. Okay, so now be careful, the derivative of a sine function give you a positive cosine function. Now that's the velocity. You can say in this sense that we already know the velocity of this object at any instant. Now we can do this further. Let's say I'm going to take the derivative further, and then I will get ax and ay. Now what's ax? Ax is given by this derivative here, and then we turn sine function into a cosine function again. Also bring out the another omega factor. So equals negative omega squared times r cosine omega t. Okay, and ay equals, now we bring out a negative sign, negative omega squared times r, and then a sine function. Okay. Now you can say we fully understand this object's motion because we know position, we know velocity, and we know the acceleration. But we can do more about this object's motion. By more, I mean we can draw the picture. We already know the picture for the vector r, the position vector r, is given by that, right? So now how about the velocity? Okay, now to do that, I need to do something here. I need to first figure out its magnitude. So let me talk about the vector v property. V's magnitude is given by square root of vx squared plus vy squared. And if I do that, I will plug in this expression. So I get omega squared r squared here, okay? And then there's a sine omega t squared. Now I'm going to add it to the by squared here, okay? And I notice that there's a common factor omega squared r squared. So I'm going to just pull it out and then keep cosine squared inside this parentheses and then take a square root. Okay, now sine squared plus cosine squared equals 1. So we know the final result here is omega times r. Okay, so now we get to the magnitude of the linear velocity v in terms of the angular velocity omega, right? And their relation is called linear and angular relation. So let me label this here, and then we'll go over this again later on. Linear angular relation. Okay, so linear v is the angular velocity times the radius r. Okay. Now how about its direction? Here's magnitude. So the direction of the v, right now we don't see that because just like the position vector, we need to write the velocity vector in the standard form, so that we know its angle with the x-axis is theta, for example here, right? It's cosine function. However, we have sine function here. Now to figure out the angle or the standard form of the velocity, I need to rewrite it this way. So equals omega r. Okay, so I'm going to get rid of negative sign, and then I'm going to write this as cosine function. Okay, and then there's still omega t here, but I'm going to plus pi over 2. I'm going to add a 90-degree angle to the omega t. Okay, so similar here, there's a sine function, and then omega turn cosine into a sine function. But in order to do that, you need to add pi over 2 to it. Okay, so that's why I can say right now I'm for the velocity vector. I have this standard form, okay, and the direction is given by this angle. So v direction is omega t plus pi over 2, okay, and this angle or the direction is with respect to the x-axis. Okay, so now let's see, how can I draw that velocity? Here is the vector for the position at angle omega t, theta equals omega t, and on the top of that I need to add pi over 2, so I need to draw, use a different color, a vector at 90-degree angle with respect to the position vector. Okay, so that'll be the velocity vector, and its magnitude is r times omega, and I don't want to draw the same length as the vector r, right, because they differ by this coefficient omega, and it could be longer or it could be shorter. So I'm going to just draw like schematically this v here. And usually when we draw the velocity, we want to move this velocity to the location of this object. So we know the object is here, right? So we're going to move it here parallel movement, okay, of the velocity vector, and that will represent the velocity vector v, and we know they have 90-degree angle. Okay, so this direction we're going to call it tangential direction of the circular path, and the direction here is called the radial direction. Radial direction is this way, okay, along the vector r. All right, that's v's property. Now how about a's property? First, magnitude. The magnitude is given by ax squared plus ay squared. So when I plug in this value, this expression, these two expressions, I get omega to the 4th power and then r squared. And then similarly, I'm going to have a cosine omega t squared plus sine omega t squared. And then they will add up to 1. So we get omega squared times r as the acceleration a's magnitude. Okay. Now if I know already v equals r omega, I can also replace omega by v, and then we will get v squared over r. Okay, so I bet some of you probably know this equation. Let's call it centripetal acceleration. Okay, and the direction, how about the direction? So I'm going to use the trick again. The previous trick is to rewrite this a in the standard form. Okay, so now we see we need to absorb this negative sign, right? So that's why I want to write this omega squared times r, and then cosine, let's keep the cosine function, but now it's omega t plus pi. Okay, and here is omega squared times r, and then sine omega t plus pi again. Okay, and you can check like these are also the trigonometry identities that I can use. Okay, now this angle will be the direction of the a, so it's omega t plus pi. Okay, that means that on the top of the angle theta that we have here for omega t, I need to add 180 degree, which means that the acceleration should be in the opposite direction of the vector r. Okay, so that's a. That's the additional angle pi. Okay, as I said, that usually we move this acceleration vector to the location of the object. So if I move it in this way and keep the same length, then I get the acceleration A, which is along the radial direction. Okay, so let me write this here. The direction here is radial. It's what we call radial direction. The velocity direction is tangential. All right, so that's the uniform circular motion. We discuss it in terms of both linear quantities and angular quantities. Okay. All right. Let's see. Now before I end this discussion for the circular motion, I want to mention this again, the linear angular relation. Sometimes it's very important to have a correct understanding between these two sets of quantities. Because we know they describe the same motion, right? So they must have some relation that we can explore. So first, the velocity here equals r times omega. Okay, so that's the first linear angular relation that we want to pay attention to. Sometimes we need to use this relation. And for the acceleration, we know acceleration A, right, is given by its magnitude is given by r omega squared. And if I want to use just the linear, okay, the linear v here, then we get v squared over r. Okay. But you may ask, didn't we define this alpha before, right? So alpha is called the angular acceleration. Now, what's the relation between alpha and A? Now, the answer is that the A that we talked about earlier, which is along the radial direction, is actually the radial acceleration. It's actually AR here. It's called the radial acceleration. Okay. Now let me draw a picture, and then you will understand that we need to define another acceleration. Now that's the x-axis, and that's O, and then the object is here, and then we already said that there's a radial acceleration AR here. Now, how about this direction? So we have a direction that we called tangential, right, previously. So now the question is there a quantity called AT? Tangential acceleration. Is there such a quantity? So the answer is yes, and we can actually relate AT to alpha. Okay, so if I start from this equation, and if I take a derivative on both sides and keeping r as a constant, then we have dv dt equals r d omega dt. Okay, now d omega dt is called alpha, right? So it's r times alpha. Okay, now this dv dt is what we call AT here. Okay. So here it is. Right, there's a tangential acceleration AT we can explore, and it's given by a similar relation that we have for the velocity. So linear acceleration AT, tangential acceleration, equals r the radius times angular acceleration alpha. Okay, so that's why we didn't talk about relation between AR and alpha, because there's no relation here, but we do have relation for AT and alpha. Now with that, we can have a complete acceleration. So if I add up AT and AR, so the total A should be AT plus AR, radial plus tangential, and it's given by this A here. Okay. Now if the object moves around the circle with such an A, then we say this kind of motion is non-uniform circular motion. And the reason for that is because now omega is not a constant. Okay, remember alpha is d omega dt, right? So you can integrate this equation, and then omega will be given by the initial omega plus alpha delta t. So it will be changing with time. Right? Omega is not a constant anymore. So that's why it's called a non-uniform circular motion. So another definition of non-uniform circular motion that's equivalent to a non-constant omega is alpha equals is not zero. Okay? If the angular acceleration is non-zero, then it's a non-uniform circular motion that we're looking at here. Okay, I hope that I made it clear that there are two sets of coordinate systems that you can use to describe circular motion, and depending on the component that the A we have here, either AR or AT, if AT, so this one is equivalent to AT non-zero. So if AT is non-zero, then we say it's non-uniform circular motion. And if AT is zero, then we have uniform circular motion that we talk about on this slide here. Okay, so AT will be zero, alpha will be zero, or equivalently, you can say omega equals constant. All right, that's all for this video. Thanks for watching.